And we are going to talk finally about the central limit theorem. So last time we kind of did our usual Z analysis. We looked at our kind of the distribution of our population. We said, okay, this looks pretty Gaussian, so we fit it with a PDF, and it looks pretty nice. So we've been working throughout this class so far that on this assumption that we're always going to be dealing with samples that are large, so n is greater than or equal to 30, and that our population would always be normally distributed. But that really limits essentially the types of analysis we can do and the types of samples and populations that we can measure. So we've really been working on and using this assumption that x bar is approximately equal to mu. But we want to basically figure out for a given population what is the uncertainty, or what's, at a certain confidence level, how can I express the true population mean as a function of x bar plus or minus sx and some other kind of parameters that we're going to talk about today via the central limit theorem without having to worry about. So we want to express the true population mean as a function of this sample mean and sample standard deviation. That's going to be the focus of today. And so without having to worry and make any assumptions about sample size or our underlying population distribution. So that's the focus, and that's why the central limit theorem is so useful and amazing. So just like we kind of talked about in the last video, we gave a little hint. We want to, again, that's the goal of this kind of lecture here. So let's go ahead and take a little deeper look at our central limit theorem. So so this is the beauty of the central limit theorem. Actually, let's go ahead and do an example. So let's say I have an example like this, and we'll switch to mathematics in a second. This is just a completely random probability distribution. So see, it's completely flat. It means it's completely random, completely stochastic. It's Monte Carlo simulations. It's a Markov process, whatever you want to call it. So I could generate this random integer. So creating my random list, it's a uniform probability distribution. They're all pretty much equal. So I can pick between 1 and 10. Everything is equally probable. So previously, I could do nothing with this data set, right? This is my population. I can't grab any samples from this because we're doing an analysis because it's not normally distributed. So let's go ahead and look at what the beauty of the central limit theorem says. So the central limit theorem, actually, let's go back to our the central limit theorem. It's a very powerful kind of idea, and that regardless of the shape of the population distribution, the distribution of the mean values. So my probability distribution of my x bars, my mean values of, again, my sample means of any given population will be normally distributed. As long as I have a large value, n greater than 20, really in this class, that's kind of the really limited central limit theorem. We're going to say n greater than 30. So let's see if that's the case. So I'm going to pick random choice from my population, my uniform population up here, 500 points. I'm going to pick 6 samples, and I'm going to calculate the mean. And then I'm going to do that twice. So I'm going to pick 6 samples, and I'm going to calculate 2 means. So if I do that, and if I plot that probability distribution here, so 2 samples at 2 means, basically. Not very good, right? But what happens if I calculate 10? So 10 means, and I plot the probability distribution. Still not too good. But if I start to get to 30, this looks a little bit more promising, right? So 30 looks normally distributed. If I do 100, if I plot 100 means, normally distributed. If I plot 200 means, you see? So my probability, basically what the central limit theorem is saying is exactly this, and we proved it. So the probability distribution of my sample means here, x bar, will be normally distributed regardless of my population distribution. This is unbelievably powerful. So we will show, so let's go ahead and let's look at another example. So that was for a uniform probability distribution. Let's say I have a chi-square distribution. So this is my population distribution. I'm going to again take randomly select and plot the probability distribution of my means. So randomly select from this distribution 30 points, calculate the mean, and repeat that 100 times. So if I do that, look at normally distributed, approximately. You can do it again. You can do it again. pretty normally distributed here. Normally distributed population, or normally distributed means. So regardless of this shape of this population, of my chi-square of my population, the means will be normally distributed. Let's look at an exponential distribution. Here's my exponential distribution. If I look at the means, again, normally distributed. What about a beta distribution? Very different from a normal distribution, but if I look and if I plot the means, normally distributed again. So you see, this is the power of the central limit theorem. That regardless of my population, so if I look at the probability distribution of my population, it could look like this. But always, if I take enough sample, if I basically grab enough x bars, where x bar, my number of samples, my number of means is greater than or equal to 30, that will give me, that will always be normally distributed if I plot those x bars. So my sample means will always be distributed. So we've proven that it works in all these different distributions. So what is the practical application to us as experimentalists? We don't need to care about what that shape of the probability of the population distribution is. So we were always saying, oh, we need to assume that this population distribution is normally distributed in order to use our z-tables. Now, we don't need to kind of care about that at all. We just need to know, basically show that the distribution of the means is normally distributed. And then we could do all of our usual kind of analysis and basically our tools moving forward. So from the central limit theorem, I'm going to flip my screen here, we can make the following definitions that we kind of hinted about last time. So now I could say that the standard deviation of the sample means is the standard deviation of my population over square root of n. So this 1 over square root of n is kind of the powerful, this is the kind of the outcome from our central limit theorem. Because basically it depends, you'll see that our estimate of the mean will get better as we increase our number of samples. We'll see that in a second. So we can plug that in, rewrite our z function here. So you see it just becomes, we're substituting in for our standard deviation again, because now we're no longer looking at the probability distribution of our population, we're looking at the probability distribution of our sample means. So where does this fall here? And this is now our sigma x bar. That's it. So we continue on, and now we can write, as we kind of looked at last time, let me erase this. So now we can write an expression for the true population mean will fall within these bounds, x bar plus or minus z c over 2 sigma over square root of n. But again, remember, we've used previously this approximation for s sub x, but now again, it is not s sub x, it is basically this would be our sample standard deviation, but now it's, again, sample standard deviation of our mean. So that's all that this is meaning. This s sub x bar, sample standard deviation of our mean values. So we just plug this in here, rewrite our expression. Again, sorry for that typo, s sub x. So our true population mean will fall within these bounds, x bar plus or minus sx over square root of n. That's it. This is kind of the result of our central limit theorem discussion. And this is the equation moving forward in this course that we'll use to kind of approximate our, basically to approximate or to kind of give our confidence bounds on where our true population mean, mu, will fall. That's it. Fun little derivation. So now we can go back to our kind of rolling particles and calculate that 95% confidence interval. And you see that basically you'll see it shrinks. We have much more confidence once we look at the sample mean. So it's just x bar plus or minus zc over 2 divided by the square root of n. So we see compared to here, excuse me, let's go back. You see here plus or minus 0.737 because it's still 2.94 back here. But look at how it shrunk. And why did it shrink like that? Well, because it shrinks by this factor of n. So that square root of 1 over n can drastically change and shrink those values. So here, if we treated basically that sample or my data list as n number, if we treated these, again, this kind of gets into this discussion we've had before in class about what constitutes a actually 138 samples, for example. What constitutes a sample, or what's a mean value versus what's a sample? So again, we could treat each of these. This is a measurement. This measurement's already kind of an average of basically my rolling parameter. Something like temperature. Temperature, once you take one temperature measurement, it's an average temperature measurement of basically wherever you're measuring that temperature. So this could be an X bar, a mean of your that you're pulling out from your data set. So that's what we're going to kind of do moving forward. So whenever you make a measurement, you can kind of assume that's basically an average value measurement. But we'll talk more about it. And again, if you have questions about what's a sample, what's a mean, we could always kind of clarify that. Again, it's a philosophical discussion. You'll fight with collaborators and reviewers and all that good stuff whenever you get into writing papers. Yeah. But yeah, that's about it. So we're going to be doing some problems now. No more definitions and derivations. Actually, one more definition, one more derivation, and a story time, and then we'll get into some problems. So I'll see you all next time. Thanks. Bye.